Welcome to NovaSleep, where you are first and foremost. This is your space to drift away while your mind explores the farthest edges of the cosmos. Tonight, we'll approach the very brink of a black hole, a frontier where light folds, time slows, and reality begins to blur. As you relax and listen, each sound and story will guide you deeper into this hidden world, until the mysteries of the universe feel as close as your own breath. By the way, if you like and subscribe to my video, this is the most effective way to support me. If you can tell me where in the world you are watching from and what time it is, I would love to read it in the comments. 1-The event horizon. As a one-way boundary, the event horizon is a geometric surface that divides space-time into two regions that cannot communicate in both directions. Outside observers can send signals inward, but trajectories that cross inward cannot return to the exterior once light cones tilt far enough to point only toward the center. This one-way behavior arises from the way gravity reshapes causality rather than from any material wall, so nothing collides with the surface in the usual sense, yet the future of any infalling world line is irreversibly confined. This boundary is a null surface in the language of general relativity, which means light itself would need to skim along it to remain there. The surface is defined globally by the total future of space-time, which makes it teleological in a technical sense since its exact position depends on what happens later. That subtlety is unfamiliar because most physical boundaries are defined locally. Approaching from outside, signals struggle to climb out as the escape routes narrow. Photons fight an ever steeper gravitational redshift while time-like paths bend inward more aggressively. The geometry does not crush an object by itself at the horizon, but it does lock the future of that object into a region that cannot influence the outside once the boundary is crossed. In practice, the boundary acts like a perfect diode for information flow. Radiation can enter, no classical information can exit. Any mechanism that appears to leak information must either exploit quantum effects far from classical intuition, or redefine what is meant by information and where it resides in the full theory of space-time and fields. 2. Time dilation near the horizon. As the gravitational field intensifies toward the horizon, the flow of time measured by a distant clock diverges from the proper time carried by an infalling clock. Signals sent outward are progressively stretched so that processes near the edge appear to slow down when viewed from far away. This is the gravitational redshift written into the ticking of clocks rather than into color alone. The effect grows without bound as the surface is approached. An object can traverse a short proper time, while an outside observer assigns an arbitrarily long coordinate time to the same motion. That difference is not an illusion from defective instruments, it is a concrete prediction from the metric that sets how space-time measures intervals. Inside the infaller's own frame, nothing singular announces the boundary. Local physics proceeds normally at modest scales because the equivalence principle protects small laboratories from uniform gravitational fields. The paradox arises only when frames with very different gravitational potentials are compared. Astrophysical accretion takes advantage of this mismatch. The inner discant appear to hang in slow motion, while the outer environment evolves on ordinary timescales. Light echoes and spectral lags carry imprints of differential time flow, allowing observers to extract information about the geometry close to the edge by reading temporal distortions like geological layers in a cliff. 3. Infinite redshift at the horizon. Photons that climb out from just above the horizon lose energy to the gravitational field and arrive with longer wavelengths than when they were emitted. The redshift factor increases as the emission point gets closer to the boundary and becomes unbounded in the mathematical limit taken exactly at the horizon. The color is stretched not by a medium, but by the shape of space-time itself. That stretching is inseparable from the slowing of clocks. A wave can be viewed as a clock that ticks with a given frequency. If time runs slower near the source, the count of ticks that reaches infinity per unit distant time drops, which is the definition of a redshift. The two descriptions are connected by the invariance of phase along the path. In accretion environments, this shift warps emission lines that originate from iron and other heavy elements. The observed profiles acquire long red tails because photons emitted from the receding and deep regions are both redshifted and Doppler dimmed. The shapes of these lines act as tomographic tools for reconstructing the space-time geometry. No classical process cancels this effect once the geometry is fixed. Only a change in the gravitational potential or in the emission radius can alter the outcome. That is why redshift measurements are such direct probes of proximity to the horizon, and why they feature so prominently in plans to map the edge with high-resolution spectroscopy. 4. The photon sphere and circular light orbits. At a specific radius outside a non-rotating black hole, there exists a precarious track where light can loop in circular orbits. This photon sphere is not a stable racetrack but a knife edge. A photon that deviates slightly inward falls toward the horizon, while a photon that moves slightly outward escapes to infinity. The orbit is an unstable saddle, not a safe lane. The presence of this radius shapes the silhouette called the shadow. Rays that skirt just outside this sphere can be bent and delayed to produce bright rings, while rays that cross inside are lost to the hole and leave a dark core. The geometry thereby acts like an optical device that carves out a persistent outline independent of many messy astrophysical details. In rotating spacetimes, the situation becomes more intricate. The photon region is warped by frame dragging so that prograde and retrograde paths differ. This asymmetry imprints subtle brightness gradients around the ring because light paths that ride with the spin can spend different amounts of time near the engine and experience different boosts. High dynamic range imaging combined with robust modelling can separate these signatures from the changing glow of turbulent plasma. The result is a new kind of measurement in which the desktop of geometry is inferred from the handwriting of light that nearly circumnavigated the abyss before reaching a telescope array on a distant planet. 5. Shadow size and silhouette of the black hole. The shadow is the dark footprint left in the sky when gravitational lensing deflects rays away from a central area. Its diameter depends mostly on the mass for non-extreme spins, which is why the outline is a clean probe of scale. This robustness makes the silhouette a preferred observable for experiments that combine data from telescopes spread across Earth. Spin and orientation still leave their marks. A rotating hole skews the rim and introduces brightness asymmetry because the approaching side of the disk is Doppler boosted. Even so, the overall size remains tied to the gravitational radius, which lets observers turn an angular measurement into a mass estimate once the distance is known independently. The Event Horizon Telescope EHT images of M87 and of Sagittarius. A star delivered the first direct assessments of this kind. The angular footprints match theoretical expectations within uncertainties that include scattering through interstellar plasma and the variable weather of the accretion flow. The agreement supports the underlying metric description. Next-generation baselines in space can tighten the picture. By extending the virtual aperture above Earth, the photon ring substructure can be resolved and the silhouette measured with far smaller systematic errors. That advance converts a suggestive shadow to a precision instrument for mapping strong gravity and testing alternatives. 6. Accretion disk inner edge and the innermost stable circular orbit. A thin disk cannot maintain stable circular motion all the way down to the horizon. The geometry admits a last orbit where centrifugal support fails to counter gravity. This innermost stable circular orbit sets a practical inner edge for much of the radiation in many regimes. Inside that radius, gas plunges inward rapidly and emits a different spectral and timing signature. The location of this boundary depends on spin. For prograde orbits around a rapidly rotating black hole, the last stable radius moves inward, allowing hotter and more efficient emission. For retrograde orbits, it moves outward. Spectral fitting that infers this radius, therefore, doubles as a spin measurement when the disk state is understood. Real disks are not static. Magnetic stresses, turbulence, and radial pressure gradients can modify where the transition becomes sharp. The result is a blurred edge whose position fluctuates with accretion rate, magnetic topology, and the presence of a compact corona. These effects complicate inference but also carry information about the engine. The practical outcome is that light curves and spectral lines encode the dance between stable orbits and rapid infall. By reading these patterns across many states, observers can reconstruct the moving boundary, like a shoreline traced by tides, turning a mathematical stability condition into an empirical ruler near the edge. 7. Hotspot orbits and quasi-periodic oscillations. Small patches of overdensity can form in the inner flow and orbit for a few cycles before shear and turbulence erase them. As these hotspots circle, Doppler boosting and lensing modulate the observed flux in a pattern that carries the orbital frequency. The result is a series of quasi-periodic oscillations that drift as the flow evolves. Because the orbital frequency rises steeply toward the center, the highest frequencies point to the smallest radii, and thus to the deepest gravitational potential sampled by visible plasma. Measuring such features gives access to the mass and SER bin once the geometry of the emitting region is constrained by independent data. In Sagittarius, a star fast flares with polarization swings have been interpreted as hotspots that orbit for minutes before fading. The polarization angle rotates because the line of sight threads different magnetic field directions along the path, and because relativistic aberration changes the apparent geometry of the field as the hotspot moves. These features are not guaranteed to appear in every source or every state, which is why they are powerful when present. They are fingerprints of transient order within a chaotic flow, brief markers that reveal how clocks tick at the brink where stable circular motion is about to give way to a plunge. 8. Relativistic beaming that brightens the approaching side of the disk. Radiation from plasma that moves at a significant fraction of light speed is not emitted evenly in all directions in the lab frame. It is focused into a cone that points roughly along the velocity vector, which is the essence of relativistic beaming. In an orbiting disk, the side moving toward the observer therefore looks brighter than the receding side. This asymmetry is reinforced by gravitational lensing and gravitational redshift. Photons from the approaching side not only gain a Doppler boost, but also travel through a less punishing redshift in many viewing geometries, while photons from the other side face the opposite combination. The result is a striking crescent where one limb dominates. The effect lets observers infer orientation and spin direction when combined with models of the flow. Persistent bright side indicates a stable orientation, while changes in the limb can reveal precession, turbulence, or the emergence of a jet base that contributes at certain frequencies. The imaging becomes a moving weather map of a relativistic atmosphere. Relativistic beaming also complicates naive interpretation, because local physics can be misread as intrinsic brightness variation rather than as a kinematic boost. Correcting for this requires careful synthesis of timing, spectral and polarization data, which is why multi-wavelength campaigns are crucial for turning pretty rings into quantitative laboratories. 9. Gravitational lensing and multiple rings near the edge. Strong gravity bends light paths so severely near the horizon that photons can loop around the black hole one or more times before escaping. Each extra loop adds another fainter ring in principle, creating a nested sequence of photon rings that converge toward the edge. These features are difficult to detect but are a clean diagnostic of the spacetime. The brightness and spacing of the rings depend on the metric and on the distribution of emitting plasma. In rotating systems, the rings are azimuthally distorted, and their relative intensities may vary around the circle because of beaming and absorption in the flow. The full pattern is therefore a joint imprint of geometry and astrophysics. Event Horizon Telescope data already hint at substructure beyond a single blurred rim. Though present sensitivity and calibration limit definitive separation, algorithms that incorporate physical priors for turbulence and magnetic fields can extract more from the same interferometric data by discouraging unphysical images while preserving genuine features. A confirmed detection of multiple rings would raise tests of gravity to a higher tier. Because the rings are largely set by geodesic structure rather than local plasma microphysics, they allow a sharp comparison between observations and predictions from general relativity and from proposed alternatives with different near-horizon behavior. 10. Polarization patterns that reveal magnetic fields at the boundary. Light becomes polarized when it passes through or is emitted by magnetized plasma, and the polarization direction is rotated by both plasma effects and gravity. Maps of polarization therefore act as compasses near the horizon, showing where magnetic fields thread the flow and how those fields are organized or tangled at the engine. The Event Horizon Telescope collaboration has produced polarization maps of M87 that trace ordered fields along the base of the jet. The alignment of vectors and their azimuthal swings agree with a picture in which rotating plasma and strong magnetic fields extract energy and collimate an outflow, while turbulence adds a textured overlay. Polarization carries timing information in addition to spatial structure. As hotspots orbit or as reconnection triggers flares, the polarization fraction and angle can change on timescales comparable to the orbital period near the inner edge. These swings are sensitive to geometry and to the way light paths wind around the hole before reaching the array. Future arrays with broader bandwidth and longer baselines will sharpen these compasses. With improved fidelity, the maps can separate competing models for how fields are anchored, whether the disk is in a magnetically arrested state, and how the jet shares power with the inner flow. turning polarization from a decorative overlay into a decisive measurement. 11. Hawking radiation from quantum vacuum fluctuations. One of the most surprising predictions about black holes does not come from general relativity but from quantum field theory. Stephen Hawking showed in the 1970s that the vacuum near the event horizon is unstable in the presence of intense gravity. What we usually think of as empty space is actually filled with temporary pairs of particles and antiparticles flickering into existence. Normally, these annihilate instantly, but near a horizon one partner can be pulled inward while the other escapes outward. To a distant observer, it looks as though the black hole itself is radiating real particles. This is called Hawking radiation, and it implies that black holes are not perfectly black. The radiation is incredibly faint for astrophysical black holes because the temperature is inversely proportional to the mass. A stellar mass black hole radiates at a temperature far lower than the cosmic microwave background, making detection essentially impossible with present technology. Only microscopic black holes, if they exist, would radiate strongly enough for their glow to stand out. That faintness, however, does not diminish the importance of the result, which blends gravity, quantum mechanics, and thermodynamics into a single phenomenon. The mere existence of Hawking radiation changes the fate of black holes. If the universe lasts long enough, every black hole will eventually evaporate away, with the smallest ones disappearing first. The lifetime of a solar mass black hole exceeds 10 to the 67th power years, an incomprehensible time span compared to the present age of the universe. Supermassive black holes live even longer, but their endgame is the same: slow erosion until nothing remains but radiation. This result forced physicists to grapple with the information paradox. If black holes evaporate, what happens to the information about what fell into them? Quantum mechanics says information cannot be destroyed, yet evaporation suggests it could vanish. This conflict has sparked some of the most profound debates in modern theoretical physics, and the resolution remains one of the great open mysteries of science. 12. Black hole temperature linked to surface gravity. Hawking's formula revealed that a black hole is characterized not just by mass, spin and charge, but also by a temperature. This is a deeply counterintuitive idea, because temperature is normally associated with random molecular motion, while a black hole seems to be pure geometry. The breakthrough was realizing that the surface gravity, the force felt by a particle hovering just above the horizon, is mathematically tied to thermodynamic temperature. The stronger the surface gravity, the hotter the black hole. This analogy is not superficial. The relationship between temperature, entropy, and surface gravity satisfies the same laws that govern ordinary thermodynamics. For example, the first law of black hole mechanics is analogous to the first law of thermodynamics, linking changes in mass to changes in area, angular momentum and electric charge. What began as a set of coincidences became a deep bridge between fundamental physics. For a massive black hole, the surface gravity is extremely small, which translates to a nearly zero temperature. A black hole at the center of a galaxy is essentially colder than the background universe, so rather than radiating away, it absorbs cosmic radiation and continues to grow. This imbalance explains why evaporation is relevant only for hypothetical tiny black holes, but not for the cosmic giants shaping galaxies. The very idea that space-time geometry can have a temperature opened up new avenues of thought. It suggests that gravity itself may be emergent from microscopic degrees of freedom, much like how temperature emerges from molecules. In this view, the event horizon behaves like a physical system with hidden structure, a clue pointing toward a deeper theory that unites relativity and quantum mechanics. 13. Bekenstein. Hawking entropy that scales with area. Jacob Bekenstein first argued that black holes must carry entropy to preserve the second law of thermodynamics. If matter with entropy falls into a black hole, and the hole had no entropy, the total entropy of the universe would decrease, violating the principle. He proposed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. Hawking's later calculations confirmed this with a precise formula. The Bekenstein-Hawking entropy is equal to 1/4 of the horizon's area, measured in Planck units. This discovery was revolutionary because it broke our intuition. In normal systems, entropy grows with volume. In black holes, it grows with surface area. That means the information capacity of a black hole is encoded on its boundary, not in its interior. This area law became the seed of the holographic principle, the idea that all of reality might be describable by information stored on a lower dimensional surface. The entropy of a black hole is enormous. A single supermassive black hole could contain more entropy than all the ordinary matter in the observable universe combined. This makes them dominant players in the thermodynamic accounting of the cosmos, especially when thinking about its ultimate fate. The fact that entropy and area are tied so tightly suggests that space-time geometry itself may be a kind of storage medium for information. Understanding what the microstates of a black hole are, what accounts for this entropy at the fundamental level, is one of the central challenges of theoretical physics, and different proposals, from string theory to loop quantum gravity, offer different answers. 14. The Bekenstein bound that limits information in a region. Bekenstein's reasoning did not stop with black holes. He realized that if entropy is bounded by surface area, then any physical system in a finite region of space must also obey a maximum information limit. This is called the Bekenstein bound. It states that the amount of information that can be stored within a region is not unlimited, but capped by the area of the boundary that encloses it, measured in Planck units. This is a radical departure from classical intuition, where one might think that packing more particles into a box simply increases information indefinitely. The bound tells us that the ultimate limit is not density of matter, but geometry of space. If you try to exceed that bound, the system collapses into a black hole whose entropy saturates the limit. The Bekenstein bound has implications far beyond astrophysics. It suggests that the universe itself is subject to an information ceiling of Thiel, and that all physical processes can be thought of in terms of information storage and transfer. In this picture, the laws of physics are constraints on information, and energy and matter are different forms of data encoded in spacetime. In modern theoretical physics, this idea forms the backbone of holography, quantum gravity research, and even speculations about reality being a kind of computation. The simple observation that entropy scales with area rather than volume reshaped our understanding of what is possible in the fabric of the cosmos. 15. The page curve that describes information release over time. The page curve is a theoretical prediction about how information should leak out of an evaporating black hole. If a black hole radiates purely thermally through Hawking radiation, then the emitted photons carry no imprint of what fell in. That would mean the information inside is lost forever, breaking the rules of quantum mechanics. Don Page, a physicist who worked with Stephen Hawking, suggested instead that if quantum mechanics is truly fundamental, then information must begin to emerge gradually as the black hole shrinks. The curve he proposed rises steeply at first, representing the increase of entanglement between radiation and the black hole, then turns downward once the black hole begins to lose more information than it can hide. This curve implies that for the first half of a black hole's life, the radiation looks thermal and informationless, but after the so-called page time, correlations build up that slowly reveal the hidden details of what went in. This behavior preserves unitarity, the principle that quantum evolution never loses information. The page curve is therefore not only a graph, but a statement about the deepest consistency of physics. Recent advances using quantum entanglement and holographic duality have supported the page curve. Calculations in simplified models show that quantum extremal surfaces can encode islands of information outside the horizon, giving the radiation hidden structure. These methods bridge ideas from quantum gravity and quantum information theory, two fields once thought far apart. The page curve is not just a mathematical curiosity. It provides a roadmap for what any future theory of quantum gravity must reproduce. If experimental evidence one day detects correlations in black hole radiation, no matter how faint, that would be a triumph, proving that even the darkest objects in the universe ultimately obey the rules of quantum coherence. 16. Scrambling time and the fast scrambler property. Black holes are thought to be the fastest scramblers of information in nature. Scrambling is not just mixing, but the rapid spreading of information across all degrees of freedom so thoroughly that no local measurement can reconstruct the original state. The scrambling time is the interval it takes for information that falls into a black hole to become distributed across its horizon degrees of freedom in such a way that it is no longer locally recoverable. Surprisingly, the scrambling time is not enormous. It scales logarithmically with the entropy of the black hole, making it extremely short for an astrophysical giant. This means that in principle, black holes process information more efficiently than any other system in the universe. They are natural fast scramblers, a property that has inspired research into quantum computers and the limits of computation itself. The concept has also appeared in discussions of chaos. A black hole is not chaotic in the usual sense of random or unpredictable motion. Instead, it saturates the bound on how quickly systems can spread quantum information, a property that makes it a kind of maximally chaotic system. This link between black holes and chaos has been explored using out-of-time order correlators, mathematical tools that measure how sensitive a system is to perturbations. The realization that black holes are optimal processors of information deepens the idea that they are not just astrophysical objects but laboratories for quantum mechanics. The same principles that govern a black hole's horizon may define the limits of all physical systems, including the most advanced technologies humans may one day build. 17. The Hayden Preskill Retrieval Thought Experiment. Imagine throwing a diary into a black hole. Classically, its information would be gone forever. But Hayden and Preskill proposed a fascinating twist. If the black hole is already past its page time, when it has radiated out half its entropy, then any new information thrown in can be scrambled and begin to leak back out almost immediately. In other words, black holes can act like mirrors that return information surprisingly quickly once they are old enough. The logic rests on two principles. Quantum mechanics is unitary and black holes are fast scramblers. If the diary's information is rapidly distributed across the horizon, then the next few quanta of Hawking radiation already contain it in coded form. Recovering it requires capturing enough of the outgoing radiation and performing a nearly impossible quantum computation, but in principle the information is there. This thought experiment challenges the image of black holes as permanent erasers. Instead, they become complex encoders that hide and then reveal information on specific timescales. The Hayden Preskill scenario thus softens the bleakness of the information paradox, showing a consistent path where nothing is truly lost, only disguised in correlations too subtle for practical observers to decode. The result is deeply provocative because it reframes black holes not as tombs of knowledge, but as participants in the cosmic bookkeeping of information. Even if the practical recovery is unattainable, the principle forces physics to respect the quantum rule. Information may be scrambled, but it can never be annihilated. 18. Black hole complementarity and dual descriptions of reality. The principle of black hole complementarity suggests us that two seemingly contradictory descriptions of a black hole can both be valid depending on the observer. To an outside observer, matter approaching the event horizon slows down, heats up and smears across the surface, never truly crossing. To the infalling observer, the crossing is smooth and unremarkable, with no drama at the boundary. These two perspectives appear incompatible, but complementarity asserts that no single observer can verify both descriptions simultaneously. The outside view preserves unitarity by encoding information on the horizon, while the inside view preserves the equivalence principle by allowing a smooth passage. Because no one can experience both, there is no contradiction in the physical predictions. This principle echoes quantum complementarity in ordinary physics, where particles can behave as both waves and particles depending on how they are measured. Just as no experiment can capture both behaviors at once, no observer can unify the two black hole perspectives. Reality is consistent but not reducible to a single classical picture. Complementarity has guided much of the modern debate about horizons and information. While new paradoxes such as the firewall challenge its sufficiency, the idea remains powerful. It may be that ultimate reality is always richer than any one description, and that horizons are where the plurality of quantum and relativistic truth is most exposed. 19. Soft hair that may carry hidden information. In the no-hair theorem, black holes are described as featureless, defined only by mass, spin, and charge. But recent proposals suggest that subtle soft hair may exist, consisting of low-energy excitations in the gravitational and electromagnetic fields around the horizon. These soft modes might provide a way to encode additional information about what has fallen in. Unlike ordinary matter hair, which the no-hair theorem excludes, soft hair operates at the level of boundary conditions and long-wavelength fields. They are delicate but in principle measurable, meaning that black holes may not be as perfectly bald as once thought. Instead, they could store faint imprints of their history in these extended structures. If soft hair is real, it offers a path to resolving the information paradox. Information might not be locked in inaccessible singularities, but stored in subtle correlations just outside the horizon. This would reconcile unitarity with the outward appearance of simplicity, preserving the consistency of quantum mechanics. The soft hair proposal is still speculative, but it has gained attention because it connects with the broader holographic idea that horizons are surfaces encoding information. Whether through soft hair, quantum entanglement, or other mechanisms, the edge of a black hole may turn out to be a richly textured recording device rather than an absolute blank. 20. Quantum hair and subtle phase correlations. Extending the idea of soft hair, some theorists suggest that black holes may carry quantum hair, subtle quantum properties that go beyond the classical description. These are not macroscopic features like magnetic fields, but delicate phase correlations hidden in the quantum state of the black hole and its radiation. The existence of quantum hair would mean that black holes are not identical even if they share the same mass, spin, and charge. Instead, their hidden quantum fingerprints would differentiate them, and in principle this could allow the recovery of information that fell in. The radiation escaping would then be entangled with these internal structures, carrying faint traces of individuality. This concept challenges the original interpretation of the no-hair theorem, which was rooted in classical physics. Quantum hair adds richness to black hole physics, suggesting that the simplicity we see is only apparent. At the quantum level, complexity remains encoded in correlations invisible to classical measurements. If confirmed, quantum hair would revolutionize our understanding of horizons. It would mean that every black hole is unique, not just in size and spin, but in its quantum identity. The horizon would not erase but encrypt, turning one of the universe's most mysterious objects into the ultimate cryptographic vault. 21. The firewall proposal that challenges smooth horizons. The firewall proposal arose as a radical attempt to reconcile the black hole information paradox. According to classical general relativity, an infalling observer should notice nothing special upon crossing the horizon. The principle of equivalence guarantees that local physics remains smooth in freefall. Yet when physicists combined this principle with unitarity from quantum mechanics and the requirement that Hawking radiation must carry information, an inconsistency appeared. The proposed resolution was shocking. Perhaps the horizon is not smooth at all, but instead is a searing wall of high-energy particles, a firewall that destroys anything trying to cross. The idea of a firewall directly violates the equivalence principle, one of the bedrocks of relativity. If true, it would mean that black holes are unlike any other region of space-time and that general relativity breaks down right at the horizon. For an observer plunging inward, rather than passing unremarkably into the interior, they would be incinerated instantly at a boundary of quantum fury. The quiet veil would be replaced by a violent barrier. This proposal split the community because it forces a choice between principles long assumed to be unshakable. Either information is lost, which quantum mechanics forbids, or horizons are no longer smooth, which relativity forbids. The firewall is a way to save unitarity at the cost of Einstein's cherished principle, and that price is steep. It calls into question the universality of freefall and the continuity of spacetime. The firewall debate has not been settled. Some theorists see it as evidence that a new paradigm is needed to unify gravity and quantum theory. Others argue that subtle entanglement structures, holographic dualities, or non-local effects can resolve the paradox without a literal firewall. Regardless of the outcome, the proposal underscores how horizons remain the testing ground where the deepest principles of physics collide. 22. The fuzzball picture that replaces the interior. The fuzzball proposal, born from string theory, suggests that black holes do not have smooth interiors at all. Instead of a singularity hidden by an event horizon, the entire region is filled with tangled strings, branes, and quantum excitations that together create a fuzzball. In this view, the horizon is not an empty boundary, but a surface where the detailed microstates of the black hole live. This idea grew out of string theory's ability to count the number of microstates corresponding to certain supersymmetric black holes. Those microstates match the entropy predicted by Bekenstein and Hawking, lending support to the claim that horizons are not featureless. If every black hole is really a fuzzball, then information is never lost. It is encoded in the specific quantum configuration of the fuzzball itself. The fuzzball picture radically changes the story of an infalling observer. Rather than floating smoothly into a silent void, they would encounter a rich quantum mess immediately upon reaching the would-be horizon. The interior is replaced by an enormous quantum structure that is not smooth spacetime at all. This eliminates the singularity problem because no single point exists where density becomes infinite. Everything is distributed through the fuzzball's fabric. Though the fuzzball idea is not universally accepted, it represents one of the boldest departures from classical intuition. If true, it suggests that the very geometry of space-time dissolves at the edge of a black hole, replaced by fundamental quantum strings. Horizons would then be not the end of knowledge, but the place where the ultimate structure of reality is woven. 23. Loop quantum gravity area quanta on the horizon. Loop quantum gravity, a rival to string theory, takes a different approach to resolving the mysteries of horizons. In this framework, space itself is quantized, made of tiny loops or spin networks. The event horizon of a black hole is not a continuous surface, but is built from discrete area quanta, each with a fundamental size determined by the Planck length. Instead of a smooth boundary, the horizon is a mosaic of minimal patches. This granularity offers a natural way to explain entropy. The Bekenstein-Hawking formula can be derived by counting the possible ways these area quanta can be arranged. Each configuration represents a microstate, and the total number of microstates produces the expected entropy proportional to the horizon's area. In this sense, the event horizon is like a cosmic pixelated screen recording the information of the black hole. If horizons are quantized, then many of the infinity's troubling black hole physics may vanish. Singularities would be replaced by regions where space-time cannot be subdivided further, preventing densities from becoming infinite. The inside of a black hole would be a domain where classical geometry no longer applies, replaced by a new kind of discrete structure. Although loop quantum gravity lacks the wide-ranging framework of string theory, its predictions about horizon discreteness remain compelling. If future experiments detect tiny signatures of area quantization, perhaps in the spectrum of black hole radiation, it would provide evidence that space itself has an atomic structure, rewriting the foundations of physics. 24. The holographic principle and boundary encoding of physics. Perhaps the most influential insight inspired by black hole horizons is the holographic principle. First proposed by Gerard T. Hooft and Leonard Susskind, it suggests that all the information contained within a volume of space can be encoded on its boundary. Black holes motivated this because their entropy scales with area, not volume. If the maximum information a black hole can hold is proportional to its surface, then reality itself may be holographic. In this view, the universe is like a giant hologram. The three-dimensional world we experience emerges from information written on a two-dimensional surface. The most precise formulation of this is the anti-de Sitter/conformal field theory, ADES/SAFT correspondence in string theory, where a gravitational system in a higher dimensional space is equivalent to a non-gravitational quantum field theory on its boundary. This duality provides a powerful toolkit. It means that questions about black holes and quantum gravity, normally impossible to compute, can sometimes be translated into questions about quantum fields on a flat surface where ordinary mathematics applies. Horizons are no longer opaque mysteries, but gateways to dual descriptions. The holographic principle is more than mathematics, it reshapes philosophy. It suggests that what we perceive as space-time may be emergent, a projection from more fundamental degrees of freedom living on boundaries. In this light, the event horizon of a black hole is not just a border, but a canvas, encoding the ultimate blueprint of reality. 25. Einstein-Rosen equals Einstein-Podolsky-Rosen link as ER equals EPR. A striking conjecture has emerged in modern theoretical physics. ER equals EPR. It proposes that Einstein-Rosen bridges, commonly known as wormholes, are deeply connected to Einstein-Podolsky-Rosen quantum entanglement. In simple terms, entangled particles may be connected by microscopic wormholes, invisible yet fundamental. This bold idea bridges two seemingly different puzzles. Wormholes arise from general relativity as shortcuts through space-time, while entanglement arises from quantum mechanics as correlations between distant particles. ER equals EPR suggests they are two faces of the same coin. If true, then space-time itself may be woven together by networks of entanglement. For black holes, this means that entanglement between Hawking radiation and the black hole interior could literally be pictured as wormhole connections. Instead of abstract correlations, the radiation may be tied back into the geometry through invisible bridges. This provides a striking visualization of how information might escape without breaking quantum rules. Although ER equals EPR remains speculative, it carries an irresistible elegance. It implies that every entangled pair is linked by a wormhole, however tiny and non-traversable. Space-time geometry and quantum entanglement are not separate concepts, but manifestations of a single, unified fabric of reality. 26. Horizon as a quantum error correcting code. One of the most fascinating modern perspectives suggests that the event horizon may function like a quantum error correcting code. In quantum computing, error-correcting codes allow fragile quantum information to be stored in such a way that even if some of the physical carriers are disturbed or lost, the overall state can still be recovered. The holographic principle, especially in its anti-de Sitter/conformal field theory formulation, shows a striking similarity. Bulk information inside a region of spacetime can be reconstructed from multiple overlapping boundary regions. This redundancy acts exactly like a quantum code. If the horizon is such a code, then information about matter falling in is never destroyed, but becomes redundantly encoded in the degrees of freedom spread across the horizon surface. Even if part of the system decoheres, the total information remains recoverable, at least in principle. This addresses the black hole information paradox without resorting to dramatic violations like firewalls or destroyed unitarity. It reframes the horizon not as a point of loss, but as a perfect encoding surface. The implications are enormous. If spacetime itself is a quantum error-correcting code, then geometry is not fundamental but emergent. The smoothness of space is an illusion created by the stability of encoded information. Distort the encoding and spacetime itself could break down. This vision ties together quantum mechanics, computation and gravity into one framework. Although still highly theoretical, the error correction view is more than metaphor. Mathematicians have constructed explicit models showing how information can be reconstructed from overlapping regions in ways that mimic a ds/c/ft duality. This may be the first glimpse of how our universe ensures that, even at the brink of a black hole, information is never truly erased, but is cleverly preserved in the most efficient code nature has ever devised. 27. Magnetically arrested disk states near the edge. Around certain black holes, accretion disks do not behave like smooth spirals of gas falling inward. Instead, magnetic fields can become so strong near the event horizon that they choke the inflow, halting matter in a turbulent standstill. This is called a magnetically arrested disk state. In this regime, magnetic pressure and gas pressure reach equilibrium, producing violent reconnection events and sudden flares of energy. In a MAD state, accretion is not steady but episodic. Gas piles up, magnetic fields snap, and then material plunges inward in bursts, releasing enormous radiation. These cycles may explain the flaring activity observed from Sagittarius, a star, the black hole at the center of the Milky Way, where sudden brightening events occur without warning. The magnetic fields act like a dam, storing energy until it is explosively released. Simulations show that MAD states are incredibly efficient at launching jets. The strong magnetic fields threading the horizon can tap into the spin of the black hole itself, funneling energy outward in narrow beams that stretch across intergalactic space. These jets are some of the most powerful structures in the universe, and their origin may lie in the balance of magnetic fields and accretion near the horizon. The study of MAD states reveals that horizons are not quiet borders but dynamic, magnetically chaotic environments. They are cosmic laboratories where plasma physics, relativity, and turbulence intersect. What looks from afar like a calm dark sphere is, up close, a storm of magnetic violence sculpting the energy output of galaxies. 28. Magnetic reconnection that powers sudden flares. Magnetic reconnection is a process where magnetic field lines, normally frozen into plasma, break and reconnect in new configurations, releasing stored energy in explosive bursts. Near a black hole's event horizon, where plasma is dense and magnetic fields are twisted by frame dragging, reconnection may occur on colossal scales. These events can accelerate particles to near light speeds and produce intense flares of X-rays and infrared radiation. Such reconnection may explain why Sagittarius, a star, sometimes erupts with sudden short-lived brightening events, even though it is usually quiet compared to active galactic nuclei. The fields become so tangled that they snap, unleashing energy that briefly lights up the darkness. This behavior mirrors solar flares in our own star, but magnified by factors of billions. Reconnection near the horizon has implications for particle acceleration throughout the universe. Jets, winds, and cosmic rays may all owe part of their origin to these invisible magnetic explosions. Unlike smooth accretion, reconnection produces irregular flickering signals, and detecting these signatures helps astronomers diagnose the magnetic life near the brink. The lesson of reconnection is that horizons are not merely passive absorbers, they actively reshape and amplify our energy through plasma dynamics. The boundary of a black hole is not emptiness. It is a stage where invisible magnetic fields dance, snap, and erupt, producing bursts that can travel across the universe to our telescopes. 29. The Blandford-Znayak mechanism that launches jets. Some of the most powerful structures in the cosmos, relativistic jets stretching thousands of light years, are thought to be powered directly by black holes. The Blandford-Znayak mechanism proposes that rotating black holes threaded by magnetic fields can act as cosmic dynamos. Energy is extracted from the spin of the black hole and funneled into collimated beams of plasma blasting outward. The physics is subtle. Frame dragging near the horizon twists magnetic field lines, inducing currents that tap the rotational energy of the black hole. Instead of the hole simply swallowing everything, it becomes a power plant, driving jets that outshine entire galaxies. Observations of quasars, blazars, and radio galaxies support this picture, with jets aligning with supermassive black holes at their cores. Simulations have shown that when accretion flows reach a May-D state, the Blandford-Znayak mechanism becomes especially efficient. In such cases, a black hole can release more energy in jets than in light from the disk itself. This explains why some active galactic nuclei appear dominated by jets, while others radiate more quietly. The mechanism ties together relativity, electromagnetism, and astrophysical observation. It reveals that horizons are not merely endpoints, but engines, extracting rotational power from the most extreme objects in existence. The darkness of a black hole is thus paradoxically responsible for some of the brightest lights in the universe. 30. The Penrose process that extracts rotational energy. Long before jets were linked to black holes, Roger Penrose proposed a mechanism by which energy could be extracted from a rotating black hole. He identified the ergosphere, a region outside the horizon where frame dragging is so extreme that no object can remain at rest relative to distant stars. In this region, it is possible for a particle to split into two, with one fragment falling into the hole carrying negative energy, while the other escapes with more energy than the original particle had. This counterintuitive process extracts energy directly from the spin of the black hole. In principle, it could continue until the black hole's rotation slows to nothing. Although the process is difficult to realize in nature with particles, it provides the conceptual foundation for mechanisms like Blandford-Znayak, which achieve extraction with electromagnetic fields and plasma. The ergosphere is a unique feature of rotating black holes, and it changes the intuitive picture of a horizon as a passive sink. Instead, the region around it becomes a place where clever configurations of particles and fields can pull energy out, turning gravity's strongest prison into a potential source of power. Though no civilization has harnessed the Penrose process, it has become a staple of theoretical physics, demonstrating that even the most forbidding objects in the cosmos can give up their energy if approached in the right way. It is a reminder that black holes are not only sinks but also sources capable of fueling the grandest displays of cosmic power. 31. Superradiance that amplifies waves around a rotating black hole. Superradiance is a phenomenon in which certain types of waves, such as electromagnetic waves, scalar waves, or even gravitational waves, can be amplified when they scatter off a rotating black hole. The effect relies on the rotational energy of the black hole being tapped through the peculiar geometry of space-time around it. When a wave with the right frequency enters the ergosphere, the region outside the event horizon where all observers are dragged in the direction of the spin, it can emerge stronger than it was when it entered, having stolen a fraction of the black hole's spin energy. The principle is similar to placing a microphone near a rotating cylinder that amplifies sound waves at certain resonant frequencies. In the case of a black hole, however, the amplification can be enormous and apply to fundamental fields. This suggests that rotating black holes are not merely passive absorbers of energy, but can act like cosmic amplifiers, feeding energy into the universe rather than swallowing it silently. Superradiance has profound consequences. If a hypothetical light particle such as an axion predicted in some extensions of the standard model of particle physics, exists. It could be trapped in orbit around a black hole and amplified into a gigantic cloud through super-radiant scattering. This would drain angular momentum from the black hole and create a halo of particles that could, in principle, be detected indirectly through radiation signatures. This process also sets theoretical limits on how fast black holes can spin. If they rotate too close to the maximum allowed speed, superradiance would drain that rotation quickly. Thus, the observed distribution of black hole spins might one day serve as evidence for or against exotic particles in the universe. The ergosphere becomes more than a region of twisted spacetime. It is a possible stage for physics beyond what has yet been observed in laboratories. 32. Axion clouds around rapidly rotating black holes. The axion is a hypothetical particle originally proposed to solve a problem in quantum chromodynamics, the theory that describes the strong nuclear force. Later, axions became prime candidates for dark matter because of their extremely light mass and weak interactions. If axions exist, rapidly rotating black holes could act as engines that amplify them into enormous clouds. Through superradiance, axions with specific wavelengths resonate with the rotation of the black hole, and the black hole's spin energy is converted into an orbiting condensate of axions. This process is not only fascinating as a concept, it could lead to observable signals. Axion clouds would emit continuous gravitational waves as they lose energy through annihilation processes or transitions between quantum states. Unlike the brief bursts from black hole mergers, these gravitational waves would be steady tones, a kind of cosmic hum detectable with future generations of observatories. If detected, such a signal would not only confirm the existence of axions, but also provide a window into the intimate dynamics of black holes. The existence of these clouds would also reshape our understanding of dark matter. Instead of being smoothly distributed through the universe, dark matter could form spectacular structures near black holes, feeding on their energy and leaving distinctive imprints on the surrounding environment. By observing black hole spins, astronomers could indirectly constrain the properties of axions. For example, if no rapidly spinning black holes are observed above a certain mass range, it might indicate that axions are draining their rotational energy. The idea that invisible, ghostly particles could gather into massive quantum clouds around the most extreme objects in the universe is a striking convergence of astrophysics and particle physics. It suggests that black holes are not only laboratories for gravity, but also detectors for the faintest whispers of the particle world. 33. The black hole bomb with a reflecting mirror thought experiment. The so-called black hole bomb is a dramatic thought experiment that builds upon the idea of superradiance. Imagine placing a perfectly reflecting mirror around a rotating black hole. Waves that undergo superradiant scattering would be amplified, reflect back toward the black hole, and scatter again, becoming stronger each time. The cycle would repeat endlessly, causing the energy to grow exponentially. Eventually, the trapped waves would extract so much rotational energy from the black hole that the system would erupt with catastrophic instability. Although such a perfect mirror does not exist in reality, the thought experiment is a vivid way of showing how unstable certain systems might be if conditions allowed. Even in nature, massive clouds of light bosons such as axions could act like partial mirrors, creating feedback loops where the wave amplification sustains itself for extended timescales. This would make black holes engines for enormous energy extraction, with their spins drained as waves roar outward. The concept of a black hole bomb highlights how horizons, combined with surrounding conditions, can lead to runaway processes. It is not just a curiosity, it sets theoretical boundaries. Nature may avoid these instabilities through subtle balancing effects, but the very possibility illustrates how black holes push physics to extremes. Such thought experiments serve a crucial purpose in theoretical physics. By imagining extreme scenarios, scientists reveal weaknesses or hidden assumptions in their equations. The black hole bomb shows how superradiance, already a subtle effect, could be amplified into a cosmic explosion if feedback is introduced. It underscores the richness of phenomena possible when rotation, gravity, and fields interact at their most intense. 34. Pair production in extreme electromagnetic fields. Near the event horizon of a black hole with strong magnetic fields, conditions can become so extreme that pairs of particles and antiparticles spontaneously appear from the vacuum. This process, called pair production, occurs when electromagnetic fields approach or exceed a critical threshold. In these regions, the vacuum itself becomes unstable, splitting into electron-positron pairs that flood the environment. This is not merely speculation. Pair production is observed in laboratory conditions, such as in particle accelerators or when lasers reach immense intensities. Near a black hole, however, the scales are vastly greater, producing showers of pairs that contribute to the plasma environment around the horizon. These pairs can feed into accretion processes, alter the magnetic structure of jets, and change the way radiation emerges from the inner regions. In extreme cases, pair production could even regulate how much matter accretes onto the black hole. If magnetic fields become too strong, they may flood the region with pairs that screen and weaken the fields, producing a feedback loop. This self-regulation may explain some of the mysterious variability seen in quasars and other active galactic nuclei. The spectacle of matter appearing spontaneously from empty space near a black hole underscores the profound interplay between quantum mechanics and relativity. It reminds us that the vacuum is not truly empty, and that black holes, by intensifying fields to unimaginable levels, bring the hidden potential of the quantum vacuum into visible reality. By the way, if you like and subscribe to my video, this is the most effective way to support me. 35. Ion line broadening produced by strong gravity. In the X-ray spectra of accreting black holes, a particularly important feature often appears: the emission line of ion at around 6.4 kilo-electron-volts. In a laboratory, this line would be sharp and narrow, but near a black hole it is distorted into a broad, skewed shape. This broadening arises because photons emitted close to the horizon experience extreme Doppler shifts from orbital motion and gravitational redshifts from escaping the deep potential well. The resulting profile is asymmetric, with a long red wing extending to lower energies. This shape is a direct fingerprint of strong gravity. By fitting models to the observed ion line profiles, astronomers can infer the radius of the innermost stable circular orbit, which in turn reveals the spin of the black hole. The faster the spin, the closer matter can orbit before plunging, and the more extreme the line shape becomes. This makes the ion line one of the most powerful diagnostic tools for studying black hole environments. It is not a mere spectral curiosity, but a window into the geometry of space-time. Observations from satellites such as XMM Newton and NuSTAR have already provided detailed measurements of ion line broadening in active galactic nuclei and X-ray binaries. The ion line thus demonstrates how black holes leave unmistakable signatures on the light that escapes their grip. Even though the horizon itself cannot be seen directly, the fingerprints of its gravity are etched into the photons we detect. Every broadened line is a silent testimony to the immense warping of space-time near the edge of the abyss. 36. Compact corona geometry above the inner disk. Near the inner edge of the accretion disk, astronomers have discovered evidence for a compact, extremely hot region of plasma known as the corona. This corona is thought to sit just above the innermost stable circular orbit, and it produces high-energy X-rays that illuminate the disk below. Unlike the vast outer disk, the corona is tiny in scale, sometimes only a few gravitational radii across, yet it dominates the energetic output. The origin of the corona's energy is still debated. Some models suggest magnetic reconnection events, others propose that turbulence funnels heat into this compact region. The corona plays a critical role in shaping the spectrum of black hole systems. When its X-rays strike the disk, they are reprocessed, producing characteristic reflection features such as broadened ion lines and a Compton hump at higher energies. These imprints allow astronomers to deduce the geometry of the corona, the inclination of the disk, and even the spin of the black hole. In this way, the corona acts like a probe, shining a flashlight onto the deepest regions of spacetime. One of the mysteries is why coronas vary so dramatically. In some systems, the corona expands into a tall lamppost shape above the black hole. In others, it collapses into a flat pancake-like region hugging the disk. These shifts may explain why black holes switch between different states of activity, from dim quiescence to powerful outbursts. The study of coronas is not just about fitting spectral models, it reveals that even in regions just outside the event horizon, matter organizes itself into distinct structures with characteristic scales. This organization suggests that black hole environments, though violent, are not pure chaos, but structured laboratories where energy is partitioned in surprising ways. 37. Disk winds and outflows that drain angular momentum. Not all the gas falling toward a black hole makes it across the event horizon. Some of it is blown outward in powerful winds launched from the disk itself. These outflows, driven by radiation pressure, magnetic forces, or thermal gradients, play a critical role in regulating how much matter reaches the black hole and how much escapes to enrich its surroundings. Disk winds have been observed in both stellar mass black hole binaries and supermassive black holes at the centers of galaxies. They manifest as blue-shifted absorption lines in X-ray and ultraviolet spectra, indicating that material is racing outward at thousands of kilometers per second. In some quasars, these winds reach relativistic speeds, approaching a significant fraction of the speed of light. The winds are more than a side effect. By removing angular momentum from the disk, they allow other gas to spiral inward more efficiently. This delicate balance between inflow and outflow determines the growth rate of black holes. Without winds, matter might pile up. With them, accretion can proceed steadily, albeit less efficiently. On cosmic scales, disk winds inject energy and metals into the interstellar medium, influencing star formation and galaxies. Black holes, therefore, are not isolated consumers of matter. They are active participants in galactic ecosystems, shaping their environments through invisible but far-reaching winds. 38. Jet collimation by helical magnetic fields. Relativistic jets are among the most spectacular features associated with black holes, extending for thousands or even millions of light years. But how do streams of plasma remain so narrow and focused across such vast distances? One leading explanation involves helical magnetic fields wound around the jet like invisible corkscrews. These fields act as guiding rails, confining and stabilizing the plasma as it accelerates outward. The evidence for helical fields comes from polarization measurements of jet radiation, which reveal ordered magnetic structures even far from the black hole. Simulations confirm that twisted magnetic fields emerging from the rotating disk and black hole can naturally collimate jets into narrow beams. Without such fields, jets would disperse quickly into diffuse clouds. Collimation is not perfect. Jets wobble, kink, and occasionally disrupt, but the presence of magnetic scaffolding explains their extraordinary reach. In some cases, jets remain collimated for millions of years, delivering energy from the center of a galaxy to its outermost halo. This process shows how black holes exert influence across cosmic scales. A structure only a few gravitational radii wide can project power across distances measured in millions of light years, all because invisible magnetic spirals hold the streams together with cosmic precision. 39. Shock fronts near the plunge region. As gas spirals inward through the accretion disk, it does not fall smoothly into the black hole. Near the innermost stable orbit, turbulence and instabilities can cause abrupt transitions, forming shock fronts where matter is compressed and heated violently. These shocks convert gravitational energy into radiation, creating bursts of high-energy emission. In simulations, shocks appear as spiraling patterns of compression waves racing around the disk. In observations, they may explain quasi-periodic oscillations or sudden changes in brightness. These signatures are windows into the last stable motions before matter crosses the horizon. Shock fronts may also play a role in particle acceleration. Just as supernova shocks accelerate cosmic rays, shocks near black holes can energize electrons to relativistic speeds, contributing to the radiation we observe. The interplay between shocks and magnetic turbulence makes the inner disk a crucible of extreme astrophysics. The existence of shock fronts illustrates that accretion is not a steady drizzle, but a violent, unstable process. The region near the horizon is a storm of waves, shocks, and flares, each event a conversion of falling matter into light before it disappears forever. 40. Chaotic turbulence that governs the last stable orbits. The final stages of accretion are governed not only by gravity, but also by turbulence. Magnetorotational instability, a mechanism where weak magnetic fields trigger exponential growth of perturbations, ensures that disks are never laminar. Instead, they boil with chaotic turbulence that transfers angular momentum outward and drives accretion inward. This turbulence is not random noise. It has structure and coherence, forming filaments, eddies, and magnetic loops. It determines how efficiently matter accretes, how much energy is dissipated, and how strong the emission is at different wavelengths. Without turbulence, accretion would stall and black holes would starve. Near the horizon, turbulence becomes even more intense. The rapid orbital shear, combined with frame dragging from spinning black holes, twists magnetic fields into knots that reconnect explosively. This makes the inner disk a cauldron of unpredictability, where bursts of radiation and flickering light curves betray the turbulent heart of the system. Understanding this turbulence is one of the major goals of high-resolution simulations. It is the hidden hand that shapes all black hole feeding and feedback. Without turbulence, horizons would remain dark. With it, they shine as some of the brightest beacons in the universe. 41. Event Horizon Telescope Photon Ring Substructure. The Event Horizon Telescope, EHT, images of M87 and Sagittarius. A star revealed blurry rings of light, but hidden within those images lies even finer detail, photon ring substructure. These are nested rings created by photons looping around the black hole multiple times before escaping. Each successive loop is fainter but sharper, encoding the exact geometry of spacetime near the horizon. Detecting these subrings requires incredible resolution, beyond what Earth-sized arrays can fully achieve. But simulations predict their existence with precision, and future improvements in very long baseline interferometry may reveal them directly. If observed, they would provide a powerful test of Einstein's equations in the strongest gravitational regime known. Photon rings are not influenced heavily by messy plasma physics. They are determined by the trajectories of light itself. This makes them clean probes of the metric, allowing scientists to distinguish between general relativity and proposed alternatives. The prospect of seeing nested photon rings excites physicists because it would be like reading the fingerprint of spacetime itself. Each ring would be a layer of information peeled from the abyss, a geometric whisper from the edge of the void. 42. The first image of the M87 black hole shadow. In April 2019, the Event Horizon Telescope collaboration released humanity's first direct image of a black hole, the shadow of the supermassive black hole in the galaxy Messier 87. The image showed a glowing crescent of light encircling a dark central region, the silhouette of the event horizon against the backdrop of infalling plasma. This achievement was historic not only because it confirmed decades of theoretical predictions, but also because it represented the largest telescope ever constructed, a virtual Earth-sized array of radio dishes working in synchrony. The success demonstrated the power of global cooperation, computation, and physics working together to pierce the most mysterious veil in the cosmos. The shadow's size matched predictions from general relativity within about 10%, a striking confirmation of Einstein's theory in a regime never before tested. The asymmetry of brightness reflected relativistic beaming, with the approaching side of the disk appearing brighter than the receding side. The M87 image was more than a picture. It was a turning point. It made tangible something long imagined and inspired new generations to push further, to capture not only still images, but moving pictures of matter, dancing at the brink of the abyss. 43. Sagittarius. A star flares that hint at reconnection. At the heart of the Milky Way lies Sagittarius, a star, a supermassive black hole about 4 million times the mass of the Sun. Unlike the hyperactive quasar black holes, Sagittarius, a star is relatively quiet, accreting at a trickle, yet it occasionally erupts in bright flares of X-ray and infrared radiation that last for hours. These flares are thought to be signatures of magnetic reconnection or hotspots orbiting near the horizon. During these events, the brightness of Sagittarius A star can increase by more than an order of magnitude, making it temporarily visible against the faint background of its usual glow. Polarization measurements during flares reveal rotating magnetic fields consistent with plasma blobs orbiting close to the event horizon and producing light that swings in polarization as they move. These flares are natural laboratories. They let astronomers watch matter in real time as it whirls through the last orbits before plunging into the abyss. By timing the oscillations and modeling the emissions, researchers can infer properties such as the black hole spin and the structure of the inner accretion flow. Sagittarius. A star flares remind us that even quiet black holes are not dormant. Beneath the calm exterior lies a restless engine, occasionally releasing bursts of energy that ripple across the galactic center and allow us a fleeting glimpse into the hidden dynamics of the horizon. 44. Yes. Very long baseline interferometry as a global camera. The Event Horizon Telescope is built on a technique called Very Long Baseline Interferometry, VLBI. In VLBI, radio telescopes separated by thousands of kilometers observe the same object simultaneously, and their signals are combined with precise timing corrections. The result is the resolution of a telescope as large as the separation between the dishes. This method turns Earth into a giant lens capable of resolving the tiny angular sizes of black hole shadows. For M87, the angular size of the shadow is about 40 microarcseconds, equivalent to seeing a tennis ball on the surface of the Moon. Achieving such resolution required linking dishes across continents, from Hawaii to Europe to the South Pole. VLBI is not just a technical feat, it is a conceptual leap. It shows that human ingenuity can build instruments on planetary scales, pushing observation to the very limits imposed by physics. The challenge lies in correlating enormous amounts of data recorded on hard drives and flown physically to central locations for combination. Future improvements may link Earth-based VLBI with space-based telescopes, extending baselines and pushing resolution even further. With this, the substructure of photon rings and the turbulence of accretion flows may come into direct view, turning theory into observation. 45 to gravitational waves from ring-down after mergers. When two black holes collide and merge, they produce a burst of gravitational waves that ripple outward across the universe. After the merger, the new black hole settles into equilibrium by vibrating like a struck bell, emitting gravitational waves in a series of damped oscillations known as the ring-down. The frequencies and damping times of these oscillations depend only on the mass and spin of the final black hole. Detecting ring-down waves provides a way to test the no-hair theorem, which states that black holes are completely characterized by only mass, spin and charge. If the observed ring-down matches the predictions of general relativity, the theorem holds. If not, it may point to exotic physics such as quantum hair or modifications to gravity. The Laser Interferometer. Gravitational Wave Observatory, LIGO, and Virgo collaborations have already detected gravitational waves from dozens of black hole mergers, including ring-down phases. Although current sensitivity is limited, future observatories such as the Laser Interferometer Space Antenna, LISA, will provide exquisite detail. Allowing precise tests of black hole vibrations, the ring-down is not only a test of theory but a dramatic cosmic sound. Each oscillation is the death cry of two black holes merging into one, an audible signature of space-time itself settling down after one of the most violent events in the universe. 46. Quasi-normal modes as signatures of true horizons. When a newly formed black hole rings down after a violent event like a merger, it does not oscillate freely in arbitrary ways. The vibrations are highly constrained, described by a discrete set of patterns called quasi-normal modes. These modes are quasi because they are not eternal. They fade away as energy is carried off by gravitational waves, but during their brief lives they carry the unmistakable fingerprint of a true event horizon. Each quasi-normal mode is determined entirely by the mass and spin of the black hole. This is profoundly important because it means that measuring them provides a direct way to test the predictions of general relativity. If the observed frequencies and decay times ever deviate from the expected pattern, it would suggest that horizons are not what Einstein's equations claim them to be, perhaps indicating exotic objects like gravastars, boson stars, or fuzzballs instead of classical black holes. In this sense, quasi-normal modes are like the voice of a black hole. By listening carefully, physicists can tell whether it is singing in Einstein's key or in some alternative register. Current detectors have only just begun to resolve these tones, but with future instruments, a full symphony of quasi-normal modes may be available for study. These modes are not just technicalities, they may be the most direct observable clue about what happens at the edge of a black hole. If horizons exist as smooth null surfaces, the modes will align with predictions. If horizons are replaced by quantum structures, echoes or shifts in the spectrum may appear. Listening to the dying vibrations of black holes could therefore answer questions too deep for telescopes alone. 47. Echo searches in gravitational wave data. While quasi-normal modes fade smoothly in general relativity, some theorists have suggested that if black holes are modified by quantum effects at the horizon, the fading signal could contain faint echoes. Instead of a clean exponential decay, the gravitational wave signal might repeat in weaker bursts, as if bouncing from some hidden structure just outside the classical horizon. These echoes would be revolutionary if detected. They would suggest that horizons are not perfectly absorbing surfaces, but that they have microscopic structure capable of reflecting or reprocessing waves. This would directly contradict the traditional picture of black holes as ultimate one-way membranes. Searches for echoes have already been carried out in data from the Laser Interferometer Gravitational Wave Observatory LIGO and Virgo. A few tentative claims have been made, but none have reached the level of firm discovery. The signals are extremely faint and easily confused with noise, but the mere possibility has fueled enormous interest. If confirmed, echoes would signal a breakthrough as profound as the discovery of gravitational waves themselves. They would mark the first experimental glimpse of quantum gravity, revealing that the smooth horizons of relativity are only approximations to a deeper, more complex reality. 48 polarimetric movies planned for next-generation arrays. The Event Horizon Telescope has already given humanity still images of black hole shadows, but the future aims much higher. Upcoming upgrades will allow polarimetric movies, time-resolved images of how polarization, and thus magnetic fields, change around the event horizon in real time. This would transform our understanding of the dynamics near the horizon. Polarization carries information about magnetic field geometry, turbulence, and particle motion. By watching polarization swing and rotate across the ring of light, astronomers will be able to trace the paths of plasma blobs as they orbit, reconnect, and plunge into the abyss. For the first time, we may see magnetic storms unfold just outside the point of no return. These movies would also let physicists distinguish between competing models of accretion and jet launching. Are jets powered primarily by magnetic reconnection, or by energy tapped from black hole spin through the Blandford-Znaiec process? Watching polarization patterns evolve may provide the decisive evidence. The dream is not only to capture static portraits, but to watch black holes as living, breathing engines. A polarimetric movie would show that the horizon is not a silent silhouette, but a dynamic frontier, with light and magnetism flickering in complex patterns around the ultimate void. 49mm windows that open a path to the edge. Observing the event horizon is not simply a matter of resolution, it also depends on choosing the right wavelength. Too short, and interstellar scattering blurs the signal. Too long, and the plasma around the black hole becomes opaque. There is a sweet spot, millimeter wavelengths, roughly 1 millimeter to a few millimeters, where the atmosphere of gas around supermassive black holes becomes transparent enough to see the silhouette. This is why the Event Horizon Telescope operates in the millimeter band. At these wavelengths, light can escape from just outside the horizon without being swallowed by plasma. This window acts like a cosmic keyhole, giving us a rare line of sight into the most hidden regions of the universe. The importance of this window cannot be overstated. Without it, the shadow of Métis 7 and Sagittarius A* would remain invisible. With it, astronomers can probe the boundary between the observable universe and the unknowable interior of black holes. Future observatories plan to expand this window by observing at multiple nearby millimeter frequencies. This will sharpen images, reduce noise, and provide tomographic information about how emission layers stack near the horizon. The millimeter window is our fragile but precious portal to the edge of space-time. 50 future space interferometers that resolve horizon dynamics. While Earth-sized arrays already achieve remarkable resolution, the next frontier is space-based very long baseline interferometry. By placing radio dishes in orbit and linking them with ground arrays, astronomers can extend baselines beyond the diameter of Earth, achieving resolution sharp enough to resolve photon ring substructures and turbulence at the horizon. Missions have been proposed to create orbital interferometers capable of observing at millimeter and sub-millimeter wavelengths. With such instruments, we could see time-resolved structures orbiting near the horizon, distinguishing plasma blobs, magnetic reconnection sites, and even the predicted multiple photon rings. The leap from blurry crescents to detailed movies would be transformative. It would turn theoretical predictions into direct observation, letting humanity watch the edge of a black hole as clearly as we watch weather systems on Earth. These instruments would not only test Einstein's theory with exquisite precision, but also search for subtle deviations hinting at new physics. The future of black hole astronomy lies not in imagination, but in constructing global and interplanetary observatories that turn the invisible into the visible. 51 naked singularity tests using lensing differences. The cosmic censorship conjecture proposes that singularities are always hidden behind horizons, but what if nature allows exceptions? A naked singularity lacking an event horizon would bend light differently from a true black hole. Instead of casting a clean shadow, it might produce unusual lensing signatures, such as additional rings or distorted brightness patterns. Astronomers have considered using gravitational lensing as a way to test for such exotic objects. If a compact object mimics a black hole in mass but produces lensing inconsistent with the presence of a horizon, it could be evidence of a naked singularity. These tests are not easy, but the principle is clear. Light is the ultimate probe of geometry. The discovery of even a single naked singularity would overturn one of the central assumptions of general relativity. It would mean that singularities, points where density becomes infinite and equations break down, can be directly exposed to the universe. This would force a fundamental reconsideration of cosmic order. Though none have been observed, naked singularities remain a possibility in some theoretical models. Lensing signatures may be our best chance to distinguish them from ordinary black holes, giving observational teeth to what has long been a purely theoretical debate. 52. Cosmic censorship that hides singularities behind horizons. The cosmic censorship conjecture, proposed by Roger Penrose, is one of the deepest guiding principles in black hole physics. It suggests that the universe forbids singularities from being exposed, cloaking them always behind event horizons. In this way, the worst breakdowns of physics are hidden from view, preserving the predictability of the universe. Without cosmic censorship, singularities could be visible, and the laws of physics could become undefined in regions accessible to observers. This would make prediction impossible, because the equations of general relativity cease to apply at a singularity. By enforcing censorship, the universe maintains order by ensuring that singularities are always out of reach. The conjecture is not proven, and certain solutions to Einstein's equations allow for the naked singularities. However, most physicists believe that realistic astrophysical processes will always produce horizons to cover them. This belief has guided decades of research, shaping expectations about what observations can reveal. If cosmic censorship is ever violated, it would not just be a curiosity, it would signify a deep crack in the foundation of general relativity. Whether nature truly obeys censorship remains one of the open questions that future observations, especially of extreme lensing events, may answer. 53. Closed time-like curves in rotating metrics. In certain mathematical solutions of Einstein's equations, particularly those describing rotating black holes, paths through spacetime called closed time-like curves appear. These are loops where an object following the curve could, in principle, return to its own past. In effect, the equations permit time travel. These closed time-like curves are not believed to exist in realistic astrophysical conditions because they would require extensions of the geometry inside the event horizon that may not be physically realizable. Still, their mathematical existence raises unsettling questions. If spacetime allows such paths, what prevents paradoxes? Physicists have proposed mechanisms like the chronology protection conjecture, Stephen Hawking's suggestion that quantum effects will always intervene to prevent time loops, but no definitive proof exists. The possibility remains that in some exotic regimes, the equations of general relativity open doors to time travel. For black holes, this idea underscores how extreme space-time geometries bend not just light but time itself. Even if closed time-like curves remain purely theoretical, they show how horizons are thresholds where the ordinary flow of time breaks down, hinting at possibilities both wondrous and dangerous. 54. Traversable wormhole proposals with quantum support. Wormholes, tunnels through spacetime connecting distant regions, are familiar in science fiction, but in general relativity they are unstable. A traversable wormhole would collapse too quickly for anything to pass through. Yet recent theoretical work suggests that quantum effects might hold wormholes open under certain conditions, making them traversable in principle. These ideas often rely on exotic negative energy, a concept allowed in quantum field theory but not yet observed in sufficient quantities. If such energy can exist, it could counteract the collapse of the wormhole throat, keeping it open long enough for travel. The mathematics of this possibility often overlaps with holography and the ER equals EPR conjecture, where wormholes are tied to entanglement. For black holes, the idea is essentially intriguing. If pairs of entangled black holes are connected by wormholes, and if negative energy could make them traversable, then horizons might not always be absolute barriers. They could instead be gateways, albeit under conditions far beyond our present reach. Though traversable wormholes remain speculative, their study stretches physics to its limits. They challenge us to ask whether space-time is more flexible than we imagine, and whether horizons that seem final might conceal tunnels into elsewhere. 55. White holes as time-reversed solutions. If a black hole is a region from which nothing can escape, a white hole is its mathematical opposite, a region into which nothing can enter, but from which matter and radiation emerge. White holes are solutions to Einstein's equations that are time-reversed versions of black holes. They are not known to exist in nature, but their possibility raises deep questions about symmetry and time in the universe. A white hole would appear as a constant outpouring of matter, but with an invisible barrier preventing anything from crossing inward. This is the mirror image of the event horizon, which allows only inward crossing. Some cosmological models even speculate that the Big Bang might resemble a white hole, an eruption of energy and matter from a boundary in time. Though no evidence for white holes exists, they remain useful thought experiments. They show how general relativity does not forbid structures that seem alien to our experience. If white holes could exist, they would redefine our understanding of causality, time's arrow, and the deep symmetry of space-time. For black hole physics, white holes represent the other side of the coin. They remind us that every abyss might have a twin, and that the mathematics of space-time contains possibilities far stranger than the objects we have yet observed. 56. Baby universe scenarios beyond the horizon. One of the boldest ideas in theoretical physics is that black holes might be the birthplaces of new universes. In these scenarios, the collapse of matter does not terminate in a singularity where all laws break down. Instead, quantum effects create a bounce, in which space-time itself continues into a new expanding region that becomes disconnected from our own. From the outside, the black hole looks like a dark, consuming void. From the inside, it may be the seed of a baby universe with its own space-time physics, and possibly even life. This possibility arises because the equations of general relativity do not forbid such continuations. In fact, some cosmologists argue that the conditions inside black holes, extreme density and curvature, mirror those of the Big Bang itself. If a black hole can pinch off into a new space-time region, then every black hole could be a cosmic womb, endlessly spawning new universes beyond our perception. The implications are staggering. It would mean that our own universe might have originated from a black hole in some larger parent universe. The Big Bang could be interpreted not as the beginning of everything, but as the moment when a black hole interior blossomed into a new cosmos. The concept unites cosmology with black hole physics in an almost poetic symmetry. Though impossible to verify directly, the baby universe hypothesis carries a strange allure. It transforms black holes from cosmic graves into cosmic cradles. The very places we imagine as final ends might also be beginnings, suggesting that the cycle of creation and destruction is written into the fabric of reality itself. 57. The universe inside a black hole conjecture. Closely related to the idea of baby universes is the notion that our entire observable universe may reside inside a black hole. In this conjecture, what we call the Big Bang was the formation of a horizon in a larger parent cosmos, and our space-time has been expanding ever since as an interior region of that black hole. From this perspective, horizons are not just astrophysical curiosities, but the scaffolding of entire universes. This idea explains one puzzling fact. The observable universe has a horizon, the cosmic microwave background, that looks mathematically similar to a black hole horizon. The geometry that encloses us on the largest scales echoes the geometry of a black hole on small scales. Perhaps this similarity is not coincidence but a clue. If true, this would radically reframe our place in the cosmos. We would not be outside observers peering at black holes in a larger universe, but inhabitants of one such interior ourselves. Every black hole we see might therefore be another cosmos, inaccessible to us but teeming with its own physics. The universe inside a black hole hypothesis is speculative, but it forces us to confront a humbling possibility. What we call the universe may not be all that exists. Horizons could be the walls of self-contained realities, multiplying across the multiverse in ways our current science can only begin to imagine. 58. Emergent spacetime from networks of entanglement. An increasingly influential idea is that spacetime itself is not fundamental but emergent, arising from the web of quantum entanglement between underlying degrees of freedom. In this picture, geometry is not built from atoms of matter, but from correlations of quantum information. The The event horizon, then, is not a physical surface but the manifestation of entanglement boundaries. This concept gained traction through the holographic principle, particularly in the anti-de Sitter/conformal field theory correspondence, where spacetime inside a gravitational bulk can be reconstructed from entanglement patterns in a lower dimensional boundary theory. The lesson is profound. Spacetime is a byproduct of quantum information, not the other way around. Near black holes, this means the smooth surface we imagine as the horizon is really an emergent structure created by entangled states. If the entanglement pattern changes, say through evaporation, then the geometry itself may change or dissolve. Horizons are not permanent fixtures of reality, but fragile manifestations of deeper laws. The idea that space and time themselves emerge from quantum entanglement redefines black holes. They become not just astrophysical objects, but central examples of how the universe fabricates geometry from information. The horizon is not merely a boundary of no return, it is the very place where the illusion of smooth spacetime breaks down into its hidden quantum code. 59. Thermodynamic membranes and horizon viscosity. A surprising approach to black holes is the membrane paradigm, which treats the horizon as if it were a physical membrane with properties such as viscosity, conductivity, and resistivity. In this model, the horizon behaves like a fluid surface that can absorb, conduct, and dissipate energy. While this is only a mathematical reformulation of Einstein's equations, it provides a strikingly intuitive way to think about the edge of a black hole. For example, the membrane can be assigned a viscosity so small that it approaches a universal quantum bound. This makes black holes appear as the most perfect fluids in nature. The surface also conducts electricity in response to external fields and drags magnetic lines as if it were a physical sheet of plasma. These fluid-like properties are not literal, the horizon is not actually a physical membrane, but the analogy works so well that it has become a powerful tool in astrophysical modelling. It allows researchers to describe interactions between black holes and surrounding fields as if they were happening at a tangible surface. The membrane paradigm emphasizes how black holes blend disparate areas of physics. They are gravitational objects, quantum silicon systems, thermodynamic entities, and fluid analogues all at once. Horizons are not only mathematical boundaries but effective surfaces that behave in ways familiar to laboratory physics. 60. The membrane paradigm as a near-horizon model. Expanding on the previous point, the membrane paradigm provides practical tools for simulating astrophysical processes near horizons. For example, when magnetic fields interact with accretion disks, it is easier to treat the horizon as a conducting surface that anchors field lines. This lets theorists model jet launching and energy extraction without needing to solve the full complexity of spacetime inside the horizon. The paradigm also gives black holes effective mechanical properties. If a small perturbation strikes the horizon, the membrane responds like a stretched viscous film, ringing with vibrations that decay over time. These responses mimic the quasi-normal modes seen in gravitational wave signals, creating a consistent picture from multiple perspectives. While the paradigm does not reveal the true microscopic structure of horizons, it bridges the gap between pure theory and astrophysical application. It is a language that allows astrophysicists to work with black holes as if they were laboratory objects, describing their interactions with light, plasma, and magnetic fields in terms that are both intuitive and predictive. In a broader sense, the membrane paradigm shows how flexible the concept of a horizon can be. Depending on the question asked, it can be treated as a thermodynamic surface, a fluid membrane, a quantum encoder, or a holographic screen. Each interpretation reveals a different facet of the same enigmatic boundary. 61. Photon angular momentum and orbital vortices near the edge. Photons near a black hole do not simply travel in straight lines. The extreme curvature of spacetime twists their trajectories, and in certain conditions, photons can acquire orbital angular momentum, spiraling around the hole in vortices of light. These orbital states, sometimes called twisted light, are not just curiosities. They encode information about the gravitational field. The existence of photon vortices means that light escaping from near the horizon is imprinted with geometric complexity. In principle, analysing the angular momentum of photons could allow astronomers to map the spacetime curvature more precisely than by studying intensity alone. This would add a new layer of detail to black hole imaging, revealing the hidden choreography of light around the edge. The idea of twisted photons also links black hole physics to optics. In laboratories, scientists create light beams with orbital angular momentum to study quantum effects and build advanced communication systems. Near horizons, nature does the same experiment on a cosmic scale, twisting photons with gravity instead of lenses. If future Earth's telescopes can measure these effects, photon vortices could become a new observational signature of strong gravity. They would demonstrate that light not only bends but swirls in the presence of a black hole, carrying away the subtle spirals of space-time itself. 62. Gravitational Faraday rotation that twists polarization. When polarized light travels through a region of curved space-time, its plane of polarization can rotate, an effect known as gravitational Faraday rotation. Around black holes, where curvature is extreme, this twisting can be significant. It alters the polarization patterns of light escaping from near the horizon, embedding the fingerprint of space-time geometry into every wave. This effect is especially relevant for interpreting polarization maps of accretion disks and jets. The observed swings in polarization are not only caused by magnetic fields, but also by space-time curvature itself. Distinguishing between the two contributions is challenging but offers a unique opportunity. By decoding polarization, astronomers can separate magnetic field dynamics from the geometry of gravity. Gravitational Faraday rotation is not just a technical complication, it is a profound probe. It shows that space-time acts like an optical medium, rotating light as it passes. The polarization angles we observe are silent records of the twisted path the photons took through curved space. In the long run, measuring gravitational Faraday rotation precisely could provide yet another test of general relativity in the strong field regime. It is another way horizons speak to us, through the silent twist of light that once grazed their edges. 63. Frame dragging that rotates local inertial frames. One of the most exotic predictions of rotating black holes is frame dragging. In the vicinity of a spinning black hole, space-time itself is dragged along with the rotation. This means that objects and even light cannot remain stationary, with respect to distant stars. They are compelled to rotate around the black hole. The effect is strongest in the ergosphere, where no observer can avoid co-rotation. Frame dragging is not just a curiosity, it directly affects orbits, accretion flows, and jet formation. The inner regions of disks precess because of it, and magnetic fields are twisted into helices that launch relativistic outflows. Even time itself is bent into spirals around the horizon. The concept was tested closer to home by the Gravity Probe B experiment, which measured the tiny frame dragging effect of Earth's rotation. Around a black hole, the effect is magnified billions of times, turning space-time into a whirlpool that drags everything with it. Frame dragging demonstrates that rotation in relativity is not confined to matter. It imprints itself on space-time itself. Near horizons, this becomes overwhelming, reshaping all motion and weaving spin into the very geometry of the universe. 64. Lens-ethering precession of inner orbits. Frame dragging leads to a specific phenomenon called lens-ethering precession. When a small body orbits close to a rotating black hole, its orbital plane does not remain fixed. Instead, it slowly precesses around the spin axis of the black hole, tracing a spiral over time. This effect influences stars orbiting Sagittarius A star and gas blobs in accretion disks. In black hole binaries, lens-ethering precession may explain quasi-periodic oscillations in X-ray light curves. As the disk wobbles under the influence of the spinning spacetime, it modulates the radiation we observe. These subtle timing patterns become indirect probes of the black hole's spin. The precession is not negligible. For orbits close to the horizon, it can be dramatic, turning what would be steady ellipses into whirling, twisting paths. In extreme cases, precession can destabilize orbits, contributing to turbulence and accretion flows. This effect highlights the unity of relativity. Rotation is not just an internal property of the black hole, but a force that reshapes motion in its vicinity. The cosmos around a spinning black hole dances to the rhythm of its spin, precessing like a cosmic gyroscope on the edge of the abyss. 65. Tidal deformation and the onset of spaghettification. As objects approach the horizon of a black hole, tidal forces become overwhelming. Gravity pulls harder on the side closer to the black hole than on the side farther away, stretching the object along the radial direction and squeezing it sideways. This differential force is the origin of the famous spaghettification effect, where matter is stretched into long, thin strands. For stellar mass black holes, tidal forces become lethal far outside the horizon, tearing apart stars and planets before they ever cross the boundary. For supermassive black holes, however, the horizon is so large that the tidal gradient is gentler. In such cases, an object could cross the horizon intact, only to be spaghettified later on the way to the singularity. Spaghettification is not just a colourful metaphor. It is a direct consequence of Einstein's equations. It shows how the geometry of spacetime translates into real physical stresses on matter. Infalling stars, disrupted by tidal forces, produce tidal disruption events that flare across the sky, betraying the hidden presence of otherwise invisible black holes. The onset of spaghettification marks the ultimate surrender to gravity. It is the moment when coherence gives way to distortion, and when the difference in gravitational pull across an object overwhelms every other force in nature. Horizons may be silent, but their approach is foreshadowed by the most violent stretching the cosmos can produce. 66. Atomic disassembly under extreme gradients. As an object moves deeper into the gravitational well of a black hole, the tidal forces do not stop at tearing the body into long spaghettified strands. They continue at the molecular and atomic levels. Chemical bonds, which normally bind atoms into stable structures, are no match for the overwhelming differential pull. Molecules are ripped apart, leaving only atoms. Yet even atoms cannot withstand the gradients indefinitely. Eventually, the forces overwhelm the electromagnetic interactions that hold electrons to nuclei. At this stage, matter becomes stripped into a plasma of free protons, neutrons, and electrons. The disassembly is relentless. What was once a star, a planet, or even a human body is reduced to its most fundamental building blocks. Unlike the tidy collisions in particle accelerators, where matter is briefly smashed into subatomic fragments, the black hole stretches the process over time and space, unravelling matter layer by layer as it falls inward. This atomic disassembly is more than a grisly fate. It is a profound lesson about the hierarchy of forces in nature. Gravity, usually the weakest force in everyday life, dominates absolutely near the horizon. The electromagnetic bonds that structure the visible universe are powerless. Black holes remind us that under the right conditions, even the strongest familiar structures collapse before the curvature of space-time. The process also raises questions about what happens to fundamental particles. Do quarks and gluons, the building blocks of protons and neutrons, remain intact until they vanish behind the horizon? Or does the extreme environment push them into exotic states, perhaps resembling the quark-gluon plasma thought to have existed in the early universe? The answer lies hidden behind the horizon, tantalizingly beyond observation. 67. Neutrino behavior in the gravitational well. Neutrinos are among the strangest particles in physics, nearly massless, electrically neutral, and capable of passing through entire planets without interacting. Yet even these elusive particles are affected by the intense gravitational pull of a black hole. Infalling neutrinos follow curved geodesics just like photons, bending and slowing relative to distant observers as they approach the event horizon. In the extreme environment of accretion disks and tidal disruption events, neutrinos may play an important role in cooling matter. As gas heats to billions of degrees, it emits neutrinos that carry energy away, influencing how material flows toward the horizon. In collapsing stars that form stellar mass black holes, neutrinos can transport enormous amounts of energy, sometimes even driving explosive outbursts. What makes neutrino behavior particularly intriguing is their quantum character. Neutrinos oscillate between different flavors as they travel, and strong gravitational fields can alter these oscillations. This means that black holes might act as cosmic laboratories for studying neutrino physics, pushing their subtle transformations into regimes we cannot replicate on Earth. Because neutrinos are so difficult to detect, observing their signatures near black holes is a monumental challenge. Yet future observatories may catch faint traces of them in conjunction with gravitational waves and electromagnetic signals. These multi-messenger detections could provide unique insight into the hidden role of neutrinos in the life and death of the matter on the brink of the abyss. 68. Plasma waves modified by spacetime curvature. The plasma near an accreting black hole is not quiet. It teems with waves, oscillations of charged particles and magnetic fields, that transport energy and momentum. In normal astrophysical plasmas, these waves are well studied, but near a horizon, the intense curvature of space-time alters their behavior in ways that remain poorly understood. For example, plasma oscillations that would normally propagate freely can be trapped or slowed by gravitational redshift. Magnetic waves, known as Alfvén waves, may be twisted by frame dragging, creating helical structures that contribute to jet formation. Even turbulence itself is reshaped by the curvature, altering how energy cascades from large scales down to small ones. This interplay between plasma physics and general relativity is at the cutting edge of research. Simulations on supercomputers attempt to capture the complex feedback loop. Curved spacetime changes plasma waves, and in turn, plasma behavior modifies the magnetic fields that shape accretion and jets. In this environment, the familiar equations of electromagnetism and fluid dynamics fuse with Einstein's field equations. The horizon becomes not only a gravitational frontier, but also a plasma laboratory, where waves that would be ordinary in space or stars take on strange, curved lives under the rule of gravity. 69 magnetic Rayleigh-Taylor instabilities at the boundary. When magnetic fields hold up layers of plasma against gravity, instabilities can occur. One of the most important is the Rayleigh-Taylor instability, which arises when a heavier fluid is supported against a lighter one. In the magnetized plasma near black holes, this instability takes on new forms, twisted by strong fields and curved spacetime. Near the event horizon, plasma supported by magnetic fields can suddenly break through in finger-like streams, plunging inward in bursts. These instabilities make accretion chaotic rather than smooth, feeding the black hole in intermittent surges. At the same time, they can eject plasma outward, seeding winds or even contributing to the launching of jets. The fingerprints of such instabilities appear in light curves and spectral variability, which show flickering and irregularities that cannot be explained by steady models. Each flicker is a sign of instability, reshaping the plasma on scales of milliseconds to hours, depending on the mass of the black hole. Rayleigh-Taylor instabilities demonstrate that even the most stable-looking cosmic engines are balanced on the edge of chaos. Horizons are not serene borders, but restless zones, where balance can collapse at any moment, turning stability into turbulence and order into explosive motion. 70 turbulent dynamos that build large-scale fields. Magnetic fields near black holes are not static. They are generated and amplified by turbulent dynamos, processes where chaotic motions of plasma stretch, twist, and fold field lines into stronger configurations. This is the same principle that powers the magnetic field of Earth and stars, but in the vicinity of black holes, the energy scales are vastly higher. Dynamo action ensures that magnetic fields near the horizon do not simply decay. Instead, turbulence continually regenerates them, sustaining the magnetic structures that drive winds, flares, and jets. Without dynamos, black holes would be far quieter. With them, horizons become hubs of electromagnetic power. These processes leave their imprint on observations. Magnetic dynamos produce fluctuations in polarization, variability in emission, and irregularities in jet structures. By studying these signs, astronomers can indirectly probe the invisible magnetic machinery close to the event horizon. Turbulent dynamos also blur the line between order and chaos. They show how randomness at small scales can generate coherent, structured fields on large scales, sustaining some of the most powerful phenomena in the universe. The horizon is not merely a place of destruction, it is also a workshop for constructing magnetic architecture on cosmic scales. 71 primordial black holes as dark matter candidates. Not all black holes are born from stars. Some may have formed in the earliest moments after the Big Bang, when density fluctuations could have collapsed directly into tiny black holes. These primordial black holes could range from subatomic size to many times the mass of the Sun. For decades, they have been proposed as possible constituents of dark matter, the mysterious substance that outweighs ordinary matter in the cosmos. If primordial black holes exist, they could explain why we observe gravitational microlensing events, temporary brightening of distant stars caused by unseen compact objects passing in front of them. They could also account for some of the gravitational wave detections of merging black holes. If pairs of primordial black holes survived from the early universe until today. However, not all mass ranges are allowed. Observations constrain many possibilities. Too many small primordial black holes would produce too much Hawking radiation. Too many large ones would disrupt galactic structure. Yet some ranges remain viable, keeping alive the possibility that black holes formed in the dawn of time make up part of the dark matter. The idea is compelling because it unites two great mysteries, black holes and dark matter, into one. If primordial black holes are real, then every galaxy could be filled with ancient relics of creation, silent witnesses to the earliest moments of the universe. 72 intermediate mass black holes in dwarf galaxies. Astronomers have discovered stellar mass black holes and supermassive black holes, but the middle ground has long been elusive. These intermediate mass black holes, ranging from hundreds to hundreds of thousands of solar masses, may lurk in dwarf galaxies and globular clusters. Evidence for them comes from unusual X-ray sources, gravitational wave events, and the dynamics of stars in compact clusters. Intermediate mass black holes are important because they may be the missing link in the growth of supermassive black holes. If galaxies began with seeds of intermediate mass, then mergers and accretion could naturally build up the giants we see today. Without them, the question of how black holes reached billions of solar masses so quickly after the Big Bang remains puzzling. Detecting these objects is difficult because they do not shine as brightly as quasars and are not as numerous as stellar remnants. Yet each new detection strengthens the case that the population exists, hidden in the quiet corners of the universe. If confirmed, intermediate mass black holes would fill in the evolutionary story of cosmic engines. They would show that horizons exist at every scale, from microscopic to galactic, each one playing a role in shaping the cosmos across time. 73 growth of supermassive black holes through chaotic accretion. The supermassive black holes in galaxy centers did not appear overnight. They grew over billions of years, swallowing stars, gas, and other black holes. But this growth was not smooth, it was chaotic, driven by collisions, galaxy mergers, and random accretion episodes. Each new feeding event added mass, altered spin, and reshaped the black hole's environment. Simulations show that chaotic accretion can spin black holes up or slow them down depending on the orientation of incoming material. Gas accreting in random directions can leave the spin moderate, while prolonged, aligned accretion can push the spin near its maximum. This explains why black holes exhibit a wide range of spin states across the universe. The chaotic growth also explains the diversity of active galactic nuclei. Some black holes blaze as quasars fed by steady torrents of gas. Others remain dim, accreting sporadically in bursts. The history of feeding leaves a permanent mark on the black hole's mass, spin, and output. Chaotic accretion reveals that horizons are not static features but evolving entities. The supermassive giants we see today are products of countless chaotic meals, each one a cosmic event written into their structure. The darkness of a black hole is not timeless, it is a living record of cosmic history. 74 feedback from jets that regulates galaxy evolution. Supermassive black holes do not just consume matter, they also give back energy in the form of jets and winds. These outflows inject enormous amounts of heat and momentum into the surrounding galaxy, a process known as feedback. Without feedback, galaxies might form stars too quickly and use up their gas. With feedback, star formation is regulated and galaxies evolve more slowly and steadily. Jets from black holes can extend far beyond their host galaxies, creating cavities in intergalactic gas, heating clusters, and altering the distribution of matter. In some cases, they quench star formation by blowing gas away. In others, they may compress gas clouds, triggering bursts of new stars. This feedback explains the observed correlation between black hole mass and galaxy properties. The growth of black holes and galaxies is intertwined. The energy released near horizons shapes entire galaxies millions of light years wide. In this way, the event horizon of a black hole, a region only a few kilometers or light hours across, exerts influence over cosmic structures spanning millions of light years. Horizons are not isolated, they are connected to the destiny of galaxies themselves. 75 Tessisal quasar flicker that marks disk state transitions. Quasars are among the brightest objects in the universe, powered by accretion onto supermassive black holes, yet their brightness is not constant. They flicker, dim, and flare on timescales from hours to millions of years. These changes are thought to reflect transitions in the state of the accretion disk, where turbulence, magnetic fields, and instabilities shift the balance between inflow and outflow. Some quasars have been observed to switch off, fading dramatically as if the feeding suddenly stopped. Others brighten unexpectedly, suggesting new inflow of gas. These transitions reveal that even the most massive engines in the cosmos are unstable, living on the edge of balance. The flickering of quasars serves as a cosmic signal of horizon activity. Each change in brightness is a distant echo of magnetic reconnection, turbulent surges, or winds reshaping the inner accretion flow. For astronomers, these variations are diagnostic tools, allowing them to peer into the processes that cannot be imaged directly. Quasar flicker demonstrates that horizons are never truly quiet. Even when they appear steady, they pulse with unseen rhythms. To watch a quasar is to watch a black hole breathe, inhaling matter and exhaling energy in cycles that light up the distant universe. 76. Recoiling black holes after asymmetric mergers. When two black holes collide, the gravitational waves they emit do not always radiate symmetrically. If more energy is emitted in one direction than the other, the newly formed black hole recoils, propelled through space like a cannonball fired by its own gravitational wave blast. This recoil can reach speeds of thousands of kilometers per second, enough to eject the black hole entirely from its host galaxy. Such recoiling black holes would carry their event horizons along, leaving behind a galaxy stripped of its central engine. Astronomers have searched for these wanderers by looking for displaced quasars, bright accretion disks that no longer sit at galactic centers. Some candidates have been found with evidence of active black holes offset from the expected location. Recoils are not just astrophysical curiosities, they are tests of general relativity's most extreme predictions. The magnitude and direction of the recoil depend on spin alignment, orbital configuration, and mass ratio of the merging pair. By observing the aftermath, scientists can reverse engineer the invisible dance that occurred just before merger. If confirmed in large numbers, recoiling black holes would change our view of galaxy evolution. They would show that horizons are not always anchored, but can be kicked across cosmic space by their own violent unions, becoming solitary wanderers carrying the memory of a collision encoded in their velocity. 77. Tidal disruption events that briefly feed the horizon. When a star strays too close to a supermassive black hole, tidal forces can rip it apart in a cataclysm known as a tidal disruption event. The star is stretched into a stream of gas that wraps around the black hole, collides with itself and forms a temporary accretion disk. For weeks or months, the black hole flares with a burst of ultraviolet and X-ray light, outshining the entire galaxy before fading back into darkness. These events are rare, but they provide some of the clearest views of horizons in action. Unlike steady quasars, which may have been active for millions of years, tidal disruption events switch on suddenly and allow astronomers to observe a black hole in the act of devouring fresh material. Each flare is like catching a predator mid-meal. The light from these events carries information about the mass and spin of the black hole, the geometry of the accretion flow, and the physics of tidal forces. In some cases, relativistic jets are launched, producing bright radio afterglows that expand into space. These jets are thought to be powered by the sudden rush of material across the horizon. Tidal disruption events are cosmic reminders that horizons are not dormant. Even quiet black holes can erupt into brilliance if an unlucky star ventures too close. They show us that behind the apparent silence of galaxies lurk engines capable of spectacular, short-lived outbursts. 78. Clock stars orbiting close to Sagittarius, a star. In the centre of our galaxy, a cluster of stars whirls around Sagittarius, a star, the supermassive black hole at the Milky Way's core. Some of these stars follow highly elliptical orbits that bring them within light days of the horizon. They act like cosmic clocks, their motions governed purely by gravity, allowing astronomers to test Einstein's theory in the strongest field accessible to direct observation. One of the most famous of these stars is S2, which completes an orbit every 16 years. When it swung close to Sagittarius, a star in 2018, astronomers measured the gravitational redshift of its light, confirming predictions of general relativity with unprecedented precision. Other stars are being tracked, and future observations may detect the subtle precession of their orbits caused by spacetime curvature. These stars are invaluable because they allow long-term, precise measurements. Unlike gas, which is chaotic and turbulent, stars provide clean test particles. Their orbital dynamics reveal the invisible mass of the black hole, the shape of space-time, and even possible deviations from general relativity. Watching these stars is like watching planets orbit a hidden sun, except this sun has no surface, only a horizon. Their graceful arcs across the sky are silent witnesses to the invisible monster shaping their destinies. 79. Precision tests of relativity with near-horizon stars. The orbits of stars around Sagittarius. A star are not just pretty demonstrations, they are precision tests of fundamental physics. By mapping their trajectories over decades, astronomers can probe subtle effects predicted by Einstein's theory, such as gravitational redshift, time dilation, and relativistic precession. Each of these effects appears most clearly near the closest approach to the horizon. Already, data from the gravity instrument on the Very Large Telescope in Chile has confirmed general relativity in this extreme environment. The redshift measured when stars like S2 pass close to the black hole matches predictions precisely. In the coming years, as more stars are tracked, it may be possible to detect even smaller deviations that could hint at new physics. Such tests are vital because they extend Einstein's theory into regimes never accessible before. Gravity around Earth and the Sun is weak compared to the pull of a supermassive black hole. By studying stars near Sagittarius, a star, astronomers are effectively stress-testing general relativity under the strongest conditions possible without plunging inside a horizon. If any deviations appear, they could point to quantum effects, modified gravity theories, or other unknown principles. Horizons are not only boundaries for matter, they are also boundaries for theories, pushing science to its absolute edge. 80. Alternatives to black holes such as gravastars. While black holes are the accepted solution to Einstein's equations, some theorists have proposed exotic alternatives. One such candidate is the gravastar, short for gravitational vacuum star. In this model, the collapse of matter does not produce a singularity and horizon, but instead a shell of ultra-dense matter surrounding a core of vacuum energy. From afar, a gravastar looks almost identical to a black hole, but crucial differences might appear near the edge. Gravastars would lack true event horizons. Instead, they would possess surfaces that could, in principle, reflect or absorb radiation differently from a horizon. They might also produce different gravitational wave signatures during mergers, potentially allowing detectors to distinguish them from classical black holes. Although no evidence for gravastars has been found, the idea serves as a reminder that black holes are not the only possible endpoints of collapse. Exotic states of matter or vacuum energy might mimic them closely enough to fool us unless we probe very carefully. If gravastars or similar objects exist, they would revolutionize astrophysics, proving that horizons are not inevitable. They would show that nature has multiple ways of balancing gravity and quantum effects, some of which may be hiding in plain sight among the black hole population we observe today. At the edge of a black hole, we confront both the silence of the unknown and the promise of discovery. The horizon is not just a boundary, it is a reminder that the universe still keeps secrets deeper than our imagination, waiting patiently for us to listen. As you drift into rest, let the thoughts stay with you. Even in the darkest places, there is structure, rhythm, and meaning. And perhaps, in sleep, the mind too explores its own horizons, quietly echoing the mysteries of the cosmos. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realize. Science is the most powerful way to understand this strangeness.